We are the Powered Nordic Ski team. We'll just introduce ourselves real quick so you know who's talking. And I guess the names are on the right underneath our pictures, but I'm Spencer Brewster.
I'm Eric Debbie.
Zach Hansen.
I'm Graham Noteboom.
I'm Mark Santo.
And I'm Anthony Snow.
And
our graduate advisor was Dr. Andrew Merriweather.
And to start with an overview of our project, the goal was to bring the sport of Nordic skiing to a population of users who previously, due to various circumstances, have limited mobility or strength in their upper body. This may take the form of limited bicep or tricep strength, hand dexterity, or lack of abdominal control. And with those injuries or limitations, they previously haven't been able to participate fully in this sport. To this point, Nordic sit skiing, which we can see an image there on our poster of people participating in that, has been either for competition only or for persons from our user base, a dependent activity in which they're either pulled or pushed along by someone else. And so with the goal of being able to allow users with the injuries I just described to independently participate in the sport, we designed the Powered Nordic Ski with an e-bike motor that amplifies the user's own input, provided through a custom lever to 4-bar linkage system. This rotational input then drives a tread system which propels the user forward. It is our hope that the Powered Nordic Ski, through programs like Tetra Adapt and Trails here at the U, will bring the opportunity for users with varying levels of spinal cord injury to independently participate in the sport and get out on the snow and enjoy a form of recreation that previously has been closed off to them.
So in the bottom left, you can see our objectives. Our main objective was to make it as safe as possible. We didn't want to have any modes of injury for the user. The biggest injury we saw, the one we saw, was pinch points. And to minimize this, we designed it similar to an elliptical, where the lever point is as low as possible to keep any potential hand slips or anything down low away from the user. Our next main objective was to make it accessible. We wanted any persons with complete tetraplegia to use it. We achieved people with partial plegia. Anybody, you can use it either pushing or pulling, which helps a lot to cater to more people. We wanted to make it durable, at least IP45, but we achieved IP65 due to our motor we got. It's just very robust. The battery casing's also very waterproof, so there's no chance of any shortages or anything. We wanted to make it modular too, so anybody could use it, from the smallest woman to the largest man, and it's very easy to adjust the lever arms any wider or taller. So, and we approximated take about 5 minutes from our assembly that we have done. We were not able to completely assemble it, but we estimate that our total weight is 70 pounds, and that's at the most. It's probably under that, and that's not a problem for the user. It's only could be a problem for the people that need to transport it to and from the mountain. As far as function goes, we wanted to make it at least 10 miles per hour. We weren't able to test it with the tread and a load on there, but our no load test speed of the motor was 13 miles per hour. So we theorized that we will be able to achieve this 10 miles per hour.
And so one of the major systems on the Nordic ski is the drivetrain, and we chose a 1,000 watt mid-drive e-bike motor, which has high efficiency, low noise, and it also has around 160 newton meters of torque. The drive tread, like a snowmobile has, um, um, which is driven by the the e-bike motor uh, th- uh, th- uh, through a high strength aluminum drive shaft and a 20 tooth drive sprocket with the 40 uh, uh, tooth sprocket on the e-bike motor, which will hand us the speed we are searching for, around 10 miles an hour. Um, uh, we have also added uh, uh, two 80-pound gas springs, which add a force to the drive tread um, on, on the snow uh, to ensure proper traction. We have also um, um, added the battery for the e-bike motor over the drive tread, which will add extra weight over the tread for traction. And we also added some swing arms, which are joined on the frame via 1/2-inch shoulder bolts. The swing arms are made out of aluminum, uh, and and we have also added tensioning brackets on the back of the swing arm to tension the drive tread.
Here, okay. With respect to the drive tread, or the swing arm, which is transparently modeled under our number 1 in the design section, if you look up to the top right under testing, you'll see the swing arm FEA. This was our performance verification of the swing arm. It was done on SolidWorks. It was modeled as a solid body of 1/4-inch T661 aluminum. The forces acting on it are the propulsion force, the force from the gas spring, and the tension bolt force. The failure criterion used was von Mises stress, which yield a maximum stress result of 2.4 KSI. When comparing that to the yield strength of 39.8, you will see that it is beyond our structural capabilities. And this was done at first due to safety reasons, because once we were to get it out and have testing done on it, we could test for cases of misuse and maybe add extra forces and then iterate the arm again, which we did not get to given the circumstances.
So if you look under the design section under number 2, you'll see the lever assembly that interfaces with this motor. As Zach mentioned earlier, one of the key purposes of this project is to provide independence to our user base. And one of the main design points is to allow some way for the user to directly interface with the system. And so we designed this lever arm assembly to have motion sort of like the handles of an elliptical, so that it would feel like you're moving ski poles. One of the benefits to this is since the arms are out of phase, it allows for users who only have pull strength or only have push strength to operate the device throughout the entire cycle, because they could pull on one lever and then pull on the other, and keep doing that. So one of the other key design features is that it's adjustable and modular. If you'll look in the diagram, in the middle of the lever assembly, there's a collar that allows for you to rotate the handles in and out to suit various body types and dimensions for a variety of users. And in figuring out how to design for all these different dimensions under the testing section and anthropometric considerations, we used the online Open Lab tools, which contains a database of US human dimensions. And so we designed the lever arms to suit a range of by deltoid breadth or shoulder width of about 15.5 inches to 21.5 inches. And we were able to accomplish that. Additionally, since the handles can be swapped in and out, you can, rather than have handles that you have to hold yourself, you can swap out handles that you can clip your hands into if the user doesn't have the finger strength to do that. And so now Spencer will tell you a little bit more about how the lever arm interfaces with the motor.
So part of the important part of the 4-bar linkage system is the way that it allows the person to put forces on the lever assembly, and that translates down into a torque that is put onto the e-bike motor. So it amplifies the force from the user and turns it into a torque onto the e-bike motor, and allows for the user to continuously push back and forth and have a rotational movement. In order to design our 4-bar linkage system and make sure that it was similar to a sit ski motion, we performed a motion analysis study. So we had a user go into a lab and perform motion capture. You can see that on the right where it says motion analysis. That graph that's on the left side of the motion analysis is a graph of the X and Y plane coordinates of a user's wrist as they perform a skiing motion. And so you can see there the person comes forward, pushes down, and then comes back up to resume the motion. Our device attempts to imitate that motion, but since we don't perform a full rotation, the user follows the same trajectory. You can see it is a similar but not quite the same motion. Part of the challenges that we dealt with was making sure that the user is able to engage their full range of motion, so arm fully extended back towards their body. And through the motion analysis, we were able to determine that a user extends about 24 inches in the horizontal direction, and our motion path follows 22.5 inches. And we were happy with the result, and we decided to keep it because we wanted to make sure that the user didn't extend it too far to the point where they were unable to pull the generate enough force to pull the lever arms back into position.
And all these components, when brought together, they're brought together with our custom seat frame that we designed, with the goal to create a comfortable experience for the user, but also to not alienate the user from the experience. As has been mentioned, everything has been either designed to the side or to be tucked away underneath the seat so that they can fully enjoy the experience of Nordic skiing. And if we can right now, Dr. Kim, we'd like to show the animation that we have prepared.
Of course. And I'm going to stop yours and
Okay.
show. Can you see it?
Yes.
Yeah.
Perfect.
As you can see here, we get that full rotational motion as the levers move back and forth, and it propels the user forward. Perfect.
Okay.
And then if I can take back control real quick.
Sure.
All right, so we're confident as a group that the work we've done with the Powered Nordic Ski will be the start of bringing the sport of Nordic skiing to the population that we've targeted. And not only will they be able to participate, but they'll be able to do so independently through our system. Future work will be focused on bringing this design to a full prototype stage. We were able to get preliminary design done and a preliminary prototype of levers interfacing with the motor, so we could confirm that they all work in conjunction. But once it's brought to a full prototype, it'll be ready for testing next winter and on the snow, so we can verify performance of traction, torque, balance of the system as a whole, as well as the speed that we're able to achieve when this system is used on the snow. And after that stage, steps could then be taken to increase the modularity of the system and integrate new functionality such as turning and sip and puff control, so that an even wider base of users than what we've accomplished can be catered to with this design. Thank you all. Are there any questions?